Alright, Chapter 4, Inductive and Capacitive Resistance. Learning objectives. Upon completion of this chapter, you'll be able to say the effectors of the inductor has changed in the current of the capacitor having changed in the voltage. Inductor has the change in current, the capacitor and the change of voltage. State the relationship between the current and voltage and inductor and capacitor. State the term of the opposition inductor and capacitor offered to AC. Write the formula of inductive capacitation reactance. State the effect of the change of the frequency, XL, XCL, XC. See the effects of change in inductance XL and change to XSC. The formula to determine the total reactance is X. They compute the total reactance in a series circuit. Indict the total resistance, capacitive, inductive. Take the determine the total opposition Z. In the AC circuit, write the formula independent of the calculated independent series circuit when values are of the reactance of the capacitor, reactor of the capacitor, reactor of the resistor. The reactor of the capacitor, the resistor of the inductor, and the resistance are given. And write the Ohm's formula to determine the voltage, current, in the AC circuit to draw finally true power, reactive power, apparent power, save of the permanent unit measurement for and formulas calculated. Either state, define, and write the formula of the power factor. Give the power factor value of the reactance and the opposition. The reactance in the ohms in the AC circuit. Compute the value of the reactance in the circuit. Say the type of the reactance and the measure connected in the circuit to correct the power factor of the unity to 1. Say the difference between the calculating impedance of the shear of the AC circuit and parallel AC circuits. Inductive and capacitive resistance. You have already learned about inductance and capacitance, and individually have behaving in the direct current circuit. In chapter, you will show the inductance, capacitance, and resistance affecting the alternating current. Inductance, alternating current. They might be the good place to recall what you've learned about in phase in chapter 1. The two things in the chapter go through the cycle together, fall together, rising together. They are in falling together and rising together are in phase. When they are out of phase, the angle, lead, or lag number of the electrical degrees which one of the values leave. The lags or other measure amount that they are out of step. The time takes in current of the inductor to build up maximum to follow the zero. The time it takes the current to an inductor to build up maximum to fall to zero is important for another reason. To illustrate a very useful characteristic inductive circuits, the conductor through the inductor always lags voltage across the inductor. A circuit having pure resistance, if such things were possible, would have the alternating current through it and the voltage all across it rising and falling together. This is illustrated in Figure 4.1a, which shows the same wave of the current and voltage purely resistive circuit having an AC source. The current and the voltage do not have the same amplitude, but they are in phase. In this case, the circuit having the inductance opposing factor of the counter EMF would be enough to keep the current remaining in phase with applied voltage. You've learned that the DC circuit containing pure inductance and current of the took time and a rising maximum even though the full applied voltage was immediately maximum. Figure 4.1b shows the wave that forms purely inductive in the AC circuit in the steps of quarter cycles. Alright, shows A, quarter cycle is E, these are in phase, I and E, which would have been like your amperes and volts in the first this shows that they are the lag between the in volts is first and second, 3/4 cycles, and also the lag and lead on the full cycle. Voltage current waves in inductive circuit. Remember, this is I believe it's AC. When AC voltage first quarter cycle 0 to 90 applied to AC voltage continually increase for the no induction circuit, but the current would be increased during the first quarter cycle. You know the circuit does have an inductance. Inductance opposed to any change. Since inductance opposed to any change in current flow, no current flow during the first quarter cycle. In the next quarter cycle, 98% and 180% of the voltage increase for the back to zero. The current begins to flow in the circuit that reaches the maximum value, but the sum of the instant voltage reaches zero. The applied voltage now begins to build up at the maximum in the other direction to be followed by the resulting current, with the voltage again reaches the maximum at the end of the third quarter at 270 degrees cycle. A value is exactly opposite to which during the first and the half cycle the applied voltage leave with the resulting current with the 1/4 90 degrees to build a complete full 30-60 cycle of the voltage. The voltage again decreases to zero. The current builds the maximum value. You must not get the idea that any of the volt values stop at the particular instance. Until the applied voltage is applied, the current voltage always changing the amplitude of the direction. As you know, the sim wave must be compared to a circle. Can be compared to a circle. Just mark off a circle in 360 degrees. You can make it mark off the time in one cycle of the sim wave into 360-degree electrical degrees. The relation is shown in Figure 4.2, referring to the figure. You can see the current is said to lag in the voltage and purely inductive circuit of not by 90 degrees. But further, referring to Figure 4.2 and the 4.1, you can see that the current voltage is said to be in phase and purely resistive current in the circuit having both resistance and inductance, and you would ask that the current lags of the voltage by amounting somewhere over the 0 to 90 degrees. Alright, simply remember, A, to help you remember the relationship of the current is the inductive circuit of the word EL, Eli, or E for the symbol of the voltage, L for the inductance, and I for the symbol of the current. So the voltage over the inductance of the current, to demonstrate that the current comes after the lag voltage of the inductor. Or inductive resistance. So you were getting a quarter phase influence, which would give you your 0 to 90. Also remember that the current lags at voltage in an inductor. Inductive resistance. When the current flow for the inductor continues to reverse itself, the K for the AC, so for the an error effectively counterforce EM5 greater than DC. The greater the amount of the inductance, the greater the opposition error effect. The faster the reversal of the current, the greater the inertial opposition. The opposing force of the inductor present the flow of the alternating current cannot be called resistance. Opposing force of the inductor present with the flow of the alternating current cannot be called resistance, since it does not result with friction within a conductor. The name of the given of it is inductive reactance, because reaction of the inductor to the change of the value of the alternating current. Inductive reactance is measured by ohms and the symbol XL, or inductive reactance. Your reactance is the X and the L is the inductor. As known, the induced voltage of the conductor is proportional to the rate of the magnetic line's force of the conductor. The greater the rate, the higher the frequency, the greater the counter electromagnetic force of the induced voltage, or increase the inductancy. Also the inductive voltage and the induced voltage increase the inductancy. The more ampere turns, the greater the counter EM force. Reactance then increase of the frequency with the increase of the inductancy. The formula inductive reactance is followed. Inductor reactance of the inductor is 2 times pi times the frequency of the alternating in hertz, which is inductance measured in coulombs in second and per seconds. L is the inductance in Henry. The following example to give the illustration of the inductance reactance. 50 hertz, 60 hertz, the inductance is 20 henries. The inductance is equal to 2 times pi times 2 times 27 to the 7th times the frequency of 60 hertz times the 20 henries, or 7,563 ohms. Capacitor and alternating current. The 4 parts of Figure 4 show the variation alternating voltage current and the capacitive circuit. For each quarter of one cycle, the solid line represented the voltage curve of the capacitor, but the dotted lines represent the current line running through the center of the 0 of the reference point from the both line of current. The both line marks off at the time of the capacitor cycle. When in terms of the electrical degrees, assume the AC voltage has the acting capacitor for some time before the time represented with the starting point of the sim wave in the figure. All right, notice that the 180 degrees, they're the voltage current. At the beginning of the first quarter of 0 to 90, voltage has just passed the 0 with an increase of the positive direction. Since the 0 point is the cheapest part of the same wave, the voltage changing with changing the greatest rate. The charging of the capacitor varies directly with the voltage. Therefore, the charge of the capacitor is always changing with the greatest rate at the beginning of the first quarter cycle. In other words, the greatest number of electrons are moving off one plate onto the other plate. Thus, the capacitor current is maximum value at part A, the figure shown. A voltage proceeds toward the maximum of 90 degrees. At the rate change becomes less and less, the current must decrease to zero. The 90 degrees of voltage across the capacitor is maximum. The capacitor is fully charged. Therefore, no further movement of the electron from plate to plate. This is when the current is 90 degrees. At the end of the first quarter cycle, the alternating voltage stops increasing in the positive direction and starts to decrease. The positive voltage, both the capacitor decrease the voltage, means that the inductive plate would just be accumulated with excessive electrons. Must lose some electrons. The current flow through the must reserve the direction. Part B figure show the current curve to below zero in the negative current direction during the second quarter cycle. At 180 degrees, the voltage drops to zero. The mean for the brief instant, but the electrons are equally distributed between the two plates. For the current maximum between the rate of the change of the charge of the voltage is maximum just after 180 degrees. The reverse polarity starts to build up. Maximum negative peak was reached for the end of the third quarter cycle, 180 to 270 degrees. During the third quarter cycle, the voltage change gradually decreases the charge by the maximum of 270 degrees. At this point, the capacitor is fully charged and capacity carries the fully impressed voltage. Because the capacitor is fully charged, no further exchange of electrons. Therefore, the current flow is zero. At this point, the condition is exactly the same. At the end of the first quarter, 90% of the polarity is reversed. Just after 270 degrees, the impressed voltage once again starts with the degree for the capacitor must lose the electron negative plate. They must discharge starting with the plate minimum rate of the flowing rays rising to the maximum. The discharge action current through the latest quarter cycle at 270 360 degrees. The impressed voltage has reached zero. So at 360 degrees, you are back at the beginning of the entire cycle. Everything starts over again. If you examine the complete voltage of the current current curve in D, you'll see that the current should also at a certain point of the certain 90 degrees ahead of the voltage because of the discharging. You know the time of the place relationship between the current and voltage, called the phase relationship of the current phase relationship of the capacitor of the circuit is exactly opposite to the inductive circuit. But the current of the capacitor leaves the voltage across the capacitor by 90 degrees. You realize the current and the voltage are both going through the individual. Remember that the current of the capacitor leaves the voltage across the capacitor by 90 degrees. You realize that the current voltage both going through the individual cycle is the same as during the period of the AC voltage is impressed. Current does not go through the part of the cycle charging the discharging stop with waiting for the voltage to catch up with the amplitude of the polarity. The voltage, the amplitude, the direction, current of the continuity of the changing the position of the perspective of each of the zero line electrical instant any of the degree between 0 and 360 they have been seen reading upward of the time degree line. The current swing of the positive of the back to the 0 degree of the negative peak of the 180 degrees not measured for the number of the electron, but the charge of the plate of the picture of the direction and strength of the current in relation to the polarity strength of the voltage across the plates. At times convenient, the word amps ice to recall the mind of the relationship of the current and voltage in capacitive circuits. The I is the symbol of the current, and the word ice leads to the coming before the symbol of EC, with of course stands for capacitive. The memory aid for the ELI. You remember the current. Remember EI. Remember the current of the voltage relationship to the inductor. You have the current and voltage in the inductor, and you also have the current in the capacitor, current in the current voltage in the capacitor. Helpful remember the phase relationship with the inductor capacitor. Since the plate of the capacitor are charging polarity same rate with the AC voltage of the capacitor seem to path the alternating current. Actually, the electrons do not path the dielectric, but they rush back and forth the plate to current the flow of the circuit. It is convenient, however, to say that the alternating current flow through the capacitor. You now know it's true that the expression avoids little trouble. The speaking current flow of the circuit containing the capacitor by same shortcut. You may see that the capacitor does not path the direct current of the both plates. The connection of the AC/DC source current will have flow and only enough to charge the capacitor, while the circuit type of the hookup circuit contains both AC and DC. Only with the AC will be passing another circuit. You now have learned two things to remember without the capacitor. Capacitor will appear to conduct an alternating current, and capacitor will not conduct a direct current. Capacitive resistance. Right. So far, you have been dealing with a capacitor T5 with the half of the AC, but only with the opposition of the alternating current has been normal circuit resistance present with the conductor. However, the capacitor had themselves over the very real opposition with the current flow. The opposition arises from the fact that given the voltage frequency, number of the electrons will go back from the plate to plate, limited with the storage ability with the capacitation of the capacitor. But the capacitor is retrieved with a great number of electrons change in plates of every cycle. Instead of the current measure for the number of electrons passing to the given point with the given type of the current is increased. Increase the frequency will decrease the opposition offered by the capacitor to the curve of the break because of the number of the electrons and capacitors capable of handling the given voltage or changing the plate that often. As a result, more electronics will be on point of given the time the greater current flow. The opposition of the capacitor offers the AC the inversely proportional frequency of the capacitation. The opposition is called the capacitive resistance. You may have capacitive resistance grew with increase of frequency over given frequency. The capacitive resistance grew the increase of the increase the capacitances. You must say that the capacitive reactance decreases the increase of the frequency given the frequency of the capacitive resistance. Reactance decreases the increases of the capacity. Symbol for the capacitive reactance is XC. Note that you understand that the capacitive resistance varies inversely with the product of the frequency capacitation. Capacitive resistance is 1 over 2t and 2 times the pi times the frequency of the combs. The capacitation in farads. That's what it's measured in. Right, the capacitive reactance in ohms is in ohms. Frequency is in hertz. The capacitation is in farads. Pi is 6.28 or 2 times 3.164. That was, I believe it's 2 times it. Yeah, so you got the diameter, you go on the circumference. For example, the problem of the capacitive resistance frequency 100 hertz. Capacity in farads 500 microfarads. Equals 32 1 over 0.314 or 30.18 or 32 ohms. Reactance, impedance, and power relationships in AC circuits. Upon the point of inductancy and capacitancy have been explained individual AC circuit. The rest of the chapter will be concerned with the combination inductance, capacitance, and resistance for the AC circuits. To explain the various properties that exist for the AC circuit on the series is RLC circuit will be used over the figure 4 with a schematic resistant inductor inductor and capacitor diagram. The RLC circuit symbol shown in figure 4.4 and marked with the general symbol as you indicate AC voltage sources. Figure 4.4 shows a series of a resistor inductor capacitor circuit. Alright, the effect of the inductive resistance coupled the current with the lag of the voltage with the capacity of the resistance current of the lead the voltage of therefore the series and the inductive resistance the capacitive reactance are exactly the opposite of the effect that will result with the two are combined. If not, hard to see net effect with the tendency to cancel each other out. The combined effect of the is equal to the difference between the value. The resultant of it is called the reactance. If it is represented with the symbol X, the expressing the symbol X is equal to the exact X is equal to the resistance of the inductor minus the capacitor, or X is equal to the X is equal to the resistance of the capacitor minus the inductor. The circuit contains 50 ohms. The inductor readings is 25 ohms. The inductor, the 50 ohms of the inducive resistance, 25 ohms of capacitive resistance, and the net resistor in the net resistance, or 50x is equal to 50 ohms minus 25 ohms, or 25 ohms inductive resistance. For practical examples, suppose you have a circuit containing 100 micro henries, or with a capacitor of 1,000 microfarads, operating at a frequency of 4 megahertz. The value of the net resistance of the reactance is 4 megahertz over 100 microhertz, capacity of 1,000 microfarads. You have the capacitation of the reactance of the inductor is 2 times the 8 times the frequency. So you get 6.8 times 4 megahertz times 100 microfarads, or 215 mega ohms. Your capacitive resistance is 1 over 2 times, 2 times the frequency times the microfarads, or the capacitation, which gives you a 1 over 0.25, 1 over 0.2512, or 39 ohms. And then you subtract the inductor minus the capacitor, and you get 2472.2 inductive reactance. Now, assume the circuit contains 100 microfarads inductor in a series of 210,000s of microfarad capacitor operating at 1 megahertz. The value of the resultant resistance is, in the case, 1 frequency is megahertz. The inductance is 1 microhenry, 100 microhenries. The capacitation is 210,000ths of a microfarad. And you get the result. The 6.2 times 1 microfarad gives you 628 ohms for your reactance inductor, and then you have your 1 over 2 times frequency times the capacitation farads. 6.28, 1 megahertz, or 10,000 microfarads, or 796 ohms. 796 ohms minus 628 equals 168 capacitive. You will now know that the case of the inductive resistance, the inductive resistance is smaller than the capacitive resistance, and therefore the subtract the capacitive resistance. There's 2 examples of the illustration. Important: the capacitive and inductive resistance combined in a series. The smaller is always subtracted from the larger. The result of reactance always takes characteristics of the large. Alright, impedance. For the study of the inductance of the capacitors, you will know that the inductive resistance and capacitive react the opposite oppose the flow of the current in the AC circuit. However, another factor of the resistance oppose the flow of the current, since the practice AC circuits containing resistance, also resistance to combine oppose the flow of the current. The combined opposition by the reactance and the resistance and the reactance is called impedance, and is represented with the symbol Z. So the value of the reactance, resistance, and reactance is both given in the ohms. It might be the first to be possible to determine the value of the impedance simply adding together. It cannot be done easily. However, it is known that the A circuit contains only resistance. The current of the voltage will be in the step this in the phase will reach the maximum voltage value in the same instant. All know that the AC circuit contains only reactance of the current with either lead or lag of the voltage 1/4 of a cycle with 90 degrees. Thus, therefore, the voltage purely reactive circuit will differ in the phase of 90 degrees from a purely resistive circuit. For the reason resistance and reactance and resistance is resistance and resistance are not combined by simply adding them. When the reactance and resistance are combined, the value of the impedance will be greater than either. It's also true that the current will be greater than either. It's true that the current will not step with the voltage, nor will it differ from the phase exactly 90 degrees of the voltage. It will somewhere between the step of the 90 degree out of step of the condition of the larger reactance compared with the reactance compared with the resistance more nearly phase the difference will approach 90 degrees. Larger resistance compared to reactance will more nearly phase the difference approach of 0 degrees. Value of resistance reactance cannot be simply added together with the impedance to find impedance. The Z because of the current of the resistor and step of the voltage across of the current, they react different 90 degrees from the voltage across it, and the two are the right angles of each of the other. They are often combined by means of the same method of construction of the right angle triangle. As soon as you find the impedance of the series of the combination of 8 ohms resistance and 5 ohms inductive resistance reactance, start the drawing of the horizontal line. The ohms representing the 8 ohms, the resistor representing 8 ohms in resistance, and the base of the triangle. The single effect of the reactance are always right angle to 90 degrees, and that of the resistance. Drawing the line at the inductance. What is it? The inductance. Shit. I'm even lost myself. Like. Resistance. The inductive resistance. Failure of the resistant reacting cannot be supplied by the finding of the impedancy of determined. As you assume the impedancy of the series of the 8 ohm, the resistant 5 ohm induction reactance, start with the drawing at the ohm with the resulting with the baseline. The inductive reactance represents 5 ohm inductance reactance with the amplitude with the triangle. This shown figure 4 or 5. Now complete the hypotenuse longest side from the triangle. This hypotenuse represents the impedance of the circuit. So your hypotenuse would be the resistance between the ohms and your high peak of inductive reactance. Vertical diagram showing the relationship of the resistance, inductive reactance, and impedance of the series of the circuit. In a series circuit. Property of the right triangle, hypotenuse is squared equals the base squared times the altitude squared, or hypotenuse equals the square root of the base squared plus the altitude squared. Applied impedance has become the impedance squared equals the resistance squared over plus the reactance squared, or impedance is equal to the square root of resistance squared plus the reactance squared, or impedance is equal to resistance squared times the reactance squared. Now suppose you are applying each a equation with a check the result with an example given below. Your resistance is 8 ohms, your reactance is 5 ohms. You have 8 ohms squared, 8, 64, 25, 89, 89 ohms square rooted. You have an impedance of 9.4 ohms. When you have the capacitive reactance to deal with the inductive repentance of the previous example, the customer had to draw the line representing with the capacitive resistance downward direction shown in figure 4. Stick of the line drawn downward capacitive resistance to indicate that the active of the direction opposing the inductive resistance was withdrawn upward with the series circuit containing the capacitive resistance equation. Finally, the impedance impedance is equal to the square root of I 8 ohms 64 and X is 5 ohms. You get 9.4 ohms. Alright, in many series of the circuits, you will find the resistance combined with both inductive reactance. So this is the should you now have the value of the reactance X is equal to the difference with the value of the inductance reactance inductive with the capacitive inductive reactance. The equation of the impedance overcame the resistor, inductor reactance, and capacitor reactance. So you'd have these impedance is equal to the square root of the resistance squared times the reactance inductive reactance time minus the inductive the capacitive inductance squared. Or Z is equal to R squared times the X reactance squared. Figure 4.7, you will see the method that will be determining the impedance for the series. In a series, the circuit consisting of resistance, inductive, and capacitive. You got assume that 10 ohms inductive with resistance, 20 ohms capacitive with the resistance are connected in a series with the 40 ohms resistance let with the horizontal line represent the resistance of the R, and the line drawn upward from the end of the resistance as represent the inductive resistance inductive resistance, and represent the capacitive reactance. Inductive reactance and the capacitive reactance, the line drawn with a downward right angle, same end of the resistor, end of the resistance. That resultant of the inductive reactance, the capacitive reactance is found by subtracting inductive reactance by the inductive capacitive reactance, resulting in an value of X. So X would equal the inductive capacitation of inductive capacitive reactance minus capacitive inductive capacitance equal 10 ohms. The line will then represent the resistance times the resultant Z would be calculated as you'd have 40 resistor ohms. So you'd have 20 minus 10 equal to 10 ohms, and then impedance is equal to 1600 plus 100 ohms with 1700 or 41.2 ohms. Alright, Ohm's law for AC. In general, Ohm's laws cannot be applied with the alternating current circuit since it does not consider the reactance with all the present such circuits. However, the modification of Ohm's law, which does take into effect with the reactance, will obtain the general law of the applicable AC circuits. Where the impedance is Z, represented by the combined opposition of all the reactance and resistance. The combined opposition of all reactance and resistance. Thus, the general flow for AC is amperes equals voltage over reactance. The general modification applied to the tolerance current flowing at the any circuit, any one of the values may be found in the equation if the others are known. For example, suppose the series circuit contains an inductor of 5 ohm resistance, 25 ohm inductive resistance, inductive reactance, and the shear of the capacitor of 15 ohm reactance, and the voltage is 50 volts. What is the current? What is the current? So you'd have 50 volts. 25 plus let's see. Resistance 5 ohm, capacitive and inductive reactance 25 ohms, and capacitive inductance, capacitive reactance 15 ohms, and voltage 50. So you'd have 25 minus 15, 10 ohms, 25 plus 100 ohms square, 25 the resistance squared times the resonant 125 ohms or 1.25 ohms resistance equal to 50 volts over 1.25 or 4.46 amps. Now suppose the circuit contains an inductor having 5 ohm resistance and 15 ohms inductive reactance, and the series capacitor has 10 ohms capacitive resistance, and if the current is 5 amperes, what is the voltage? The resistance is 5 ohms. The capacitation, the inductive reactance 15. The capacitor reactance is 10 ohms, and your amperes is 5 amps. So you have 15 minus 10 will give you 5 amps resonant. The impedance is 25 times 25, 50. 50 squared is 707. So you'd have the voltage equal to 5 amps times 707, 35.35 volts power. All right, power and AC circuits. You know that the direct current circuit is power is equal to the voltage time of the current, but the power is equal to the voltage times the amp. The voltage is applied by the circuit produced the current with 10 amp of the the power is 1,000 watts. And this is true with the AC current when the current and the voltage are in phase. This is when the circuit is effectively resistive. If the AC circuit contains reactance, the current, if the AC current contains reactance, the current will lead or lag with the voltage in a certain amount with the phase angle. When the current is out of phase with the voltage, power indicated product applied with the voltage total current gives only what is known as the apparent power. The true power depends upon the phase angle between the current and the voltage symbol. Greek phase for angle is the theta. For phase angle, the theta. When the alternating voltage is increased with the capacitor, power is taken from the source of the store, but the capacitor voltage increased to 0 to the maximum. When the impressed the voltage increase the maximum value to 0, the capacitor discharge returns the power to the source. Likewise, the current is the inductor increases the 0 value to maximum value field around the inductor because it builds up to maximum. When the current decreases to maximum from the maximum to the 0, the field collapses, returns the power to the source. You can see that therefore the no power up in their case, since the power alternately flows to and from the source, the power that is returned to the source relative to components or circuit is called reactive power. In pure resistive circuits, all of the power consumed with the none of the return of the source, and in pure reactive circuit, with the no power is consumed, all of the power is returned from to the source of the power. And the circuits which contains both resistant and reactive, there therefore must be some of the power dissipated with the resistance as well as some of the return from the source of the reactance. In Figure 4 and 9, you can see that the relationship among the voltage current and the power in such a circuit, the power of for the part of the power curve shown below the horizontal reference line resulting in multiple powers instantaneous. Alright, the value of the current negative instantaneous value of the voltage, vice versa, is known as the product of obtained with the multiplying positive or negative value of the voltage. Therefore, the power is installed with the most considered negative power. In other words, during this time, the reactance was returning power to the source. So you have a voltage power power and current, and they all step off at different lengths. Notice the current and the power are also have their own in phase, and voltage and power have their own phase, and they also both lag and lead. For instantaneous power, the circuit is equal to the product of applied voltage of the current through the circuit. The voltage current is the same polarity. They are acting together to take the power, but the source of the polarities are unlikely. They are acting opposition power that may be returned to the source briefly, and the AC circuit which containing the reactance as well. The resistance apparent power is reduced to the power returned to the source, so the circuit is net power. The true power always an apparent power. Alright, calculating true power AC. And let's just see how long the tape is. It's a half an hour. I'm going to cut it, this chapter 4, into different parts. We'll see you tomorrow.